Well, we're somewhat back to square one on the power supply. I've learned a lot about high current and control, and unfortunately, controlling 36 to 40 amps is not quite as straightforward as you would hope. A lot of trouble happens in the transistor. Once you turn on, you can't turn off, and that's due to a lot of effects. Some of it being quantum related. Um, Other effects are you've got these devices all operating in parallel, and anytime you operate a device in parallel, you run into a situation where you can have current hogging, and that's because each device, because it's cut out of a wafer, they're they may come from the same wafer, but they've all gotten diffused a little bit differently. They're approximately the same, but they still have subtle variations in their doping, and that's at the atomic level. So as we get closer to their maximum, um, we're not even getting close to their maximum actually. Um, what we're trying to do is we're trying to do linear control, so we're not quite saturated until the power supply is fully on, but we don't necessarily want to be fully on when we're controlling the transistor, because we want control. We want to be able to vary that from 0 to maximum. And you can have a situation where you are trying to turn off and the transistor just won't turn off. It's stuck on. And so most of them will turn off, but you'll have one that's still on, and it's still conducting, and it may be conducting 6 amps when you're trying to control 20. So in order to mitigate that, we have to use more transistors. So that's what we're aiming for here, and we're gonna do a redesign here. So instead of trying to control 20 or 30 amps with the 6 transistors that we were aiming for, we found out that we're producing way too much thermal energy to dissipate in the heat sink. We've got way too much thermal rise too fast. We've got full thermal at 30 seconds, so we cannot tolerate that. That's not a usable power supply. We need to be able to survive torture testing more than 30 seconds. That's not a torture test. We need continuous usage throughout the torture test to survive. We're talking like days here. Talking more than 100 hours at least throughout a torture test in order to be a viable product here. So what we're doing is we're going with more volume of semiconductor in order to pass those joules of energy, and we're spreading out the basically the resistivity of the junction. We're spreading that out with more volume, because essentially what we're trying to do is we're trying to pass a fire hydrant worth of current through a garden hose, and of course a garden hose is not going to tolerate that. It would explode. In our case, we have thermal rise, which is the product of the current flowing through a resistive element, semiconductor. So in order to get around that, we are going with 18 transistors, and the transistors I was trying to use before have a relatively high turn-on voltage. They're about 1.6 volts to saturation. and that's a problem. So we're going to use similar. We're not going to use the 6341, although I love this one. This is a great transistor. We're going to use another transistor, and we're going to use 18 of them. This is just here for demonstration's sake. We made a drill pattern, and we have a key. So they're spaced 1.2 inches apart, and this is a real problem because I was trying to go from the data sheet for the transistor, the dimensions, and the dimensions just were not matching up to where the pins are. And so this is a first attempt, this is a second attempt, and I know the data sheet is all the way down to the thousandths, but I tell you, I was using gauge blocks and almost everything at my disposal to get these holes in the exact right position, down to maybe a thou or two. And I don't care what people say about that data sheet, it's not exactly right. And that's what I would refer to as the cost of admission. Now, what does that mean? It means if you want to get into doing these things, if you want to participate in design or building your own equipment, then there's a cost of admission. So that's tooling, research, burning parts up, throwing stuff away. It's all the price of admission here. So figuring out that the numbers aren't exactly right, and having to machine and remachine and do things over and over again when the information should be transparent and upfront, and it's not, that's the price of admission. So what we're going to do is we have these blanks here. We have our tool or our tool guide here, and we're going to use our guide in order to put a pattern of transistor mounts in here, and then these will get welded onto some lacing tape on here. Get out of here. These will be welded. They'll be cut down to 11, of course, first, and then they'll be welded into the heat sink in order to provide two mounts for power transistors. And I'm hoping, because we're spreading out our thermal load and our quote-unquote resistivity in the device will be hopefully 1/10 of what it was here. I haven't characterized my past transistor yet, so I don't know what its collector resistance is just yet. I'll have to do that. Effectively, we'll have 18 of them in parallel, so I don't know what the extrapolated collector resistance is going to be. But we'll have 2 of these paddles and 18 transistors, and then again we'll have a circuit board mounted to the backside here, and that's going to be complicated because each circuit board, there's going to be 2, they both need to pass 20 amps apiece, potentially 25, because we'll want this to be able to survive a 50 amp load. So the collector side has to be able to pass 50 amps. The emitter connections will be 0.1 ohm resistors, so each one of the emitter connections will only have to pass 3.5 amps max, worst case, actually like 2.9, but Each emitter will be passing 2.9 amps. So the distributed load through the emitters is not so severe, but the emitter connection, the emitter return connection, will also require some severe trace thickness. So we're going to have to work on how the circuit board gets laid out for the emitter return path. And we also found that we can cause damage to the semiconductors if we don't account for the base current, and we really need to do that. So the bases, instead of just being jumpered, they will get a 1 ohm, each one will get a 1 ohm current limiting resistor, so that when we force the transistors into saturation, we can force them into hard saturation, and we won't have we won't cause damage to the base due to excessive current. So that's a design change. We'll still have 300 ohm resistors from base to emitter, so that needs to be worked into. You can see there's some slight discoloration there, and that's because of the current that's flowing into this board. So we don't want any of the resistors experiencing discoloration or overstress at its infancy. We want this product to last a long time. We want this product to live hopefully 30 years in service without any issues, which is a tall order considering that this is a new thing that I've never done. Bear in mind that the high current stuff, it doesn't exactly scale. If you are trying to scale it, I would go with no more than 3 amps per transistor, and I would look at your turn-on voltages. You want them to be about 1 volt. You don't want a 1.2 or 1.4 volt turn-on voltage, because the less the transistor is is farther away from saturating, the more it's going to act like a resistor. And so you're looking at a situation where you're going to be creating a lot more heat in the device, and we want to avoid the heat while controlling the current at the same time. It's a pretty hard balance to meet. Now, if we were pulsing these things, it wouldn't be a problem, because we would turn hard on and then we would turn hard off, and we're discharging the base, so we're pulling all the charges out of the base and we're shutting the device off. But in this regulator design, the base isn't being depleted by those charges. It's being shut off what you would consider gradually. It's not being shut off in a microsecond. So the charges are stuck where they are in the device, essentially, and there's no, for as far as the device is concerned, it doesn't look like the charges are going back to their depletion zones. There's essentially the recovery time for the device is infinite when we're doing linear control. If it were pulsed, then it would be a few microseconds for a really slow device for those charges to go back through depletion zones and for the device to shut off. So essentially, we're not hard shutting off the device. It's still partially on, and it's on just enough at 0.5 or 0.65. Well, it's not 0.65, it'd be fully on, but it's just on enough to still pass current. And if you imagine we have all of this current on the collector side that's trying to reach the emitter side, it wants to pass through the collector to the emitter into the load. So we're trying to hold that current back. And if we don't spread out the transistor volume, then we won't, our effective holding back power is not there. So it's a very poor explanation, but you can research this more on your own time. I've found experimentally that, and through validation of another power supply, here's the part of the experiment. So we've got 11 transistors here, and we put it's 32 amps through 11 transistors. We had no problem controlling there. So moving back to here, so going from 11 to 18, we're going to have appropriate control, appropriate thermal load, and plenty of safety margin for high currents at lower voltages for heavier loads like a 0.5 ohm load at low voltage. So if you're going to design a power supply for very high currents, well, this 30 amps is high current to me, but your primary killer is going to be cost, because even the cheaper transistors, you're looking at $8 a piece, and this is typically why they go SCR on the output instead of trying to actually regulate it. But I didn't want to get into microprocessor control and timing and all that other crap. I wanted to scale up a low current 5 to 10 amp power supply up to 30 amp range, but it's proving to be very very involved. So that's it for now. We will drill these dudes out and then machine them back to where they need to be so that the transistors line up where we want them to be, and then we'll think about the circuit board layout and we'll go from there. Once that's all figured out, then these guys will get welded on, and we'll make many more mistakes, I'm sure, but we'll see how it goes. And that's it for now.